Right, this is 2.2.1 lesson 2. Today we're going to talk about the threshold frequency. We're going to also compare what an EK to photon frequency graph looks like for different materials. And we're going to look at stopping potential and what that means. So first of all, if we are using photons for the photoelectric experiment at the threshold frequency, that means that the kinetic energy of our electrons will be 0 if we are exactly at the threshold frequency. So at exactly the threshold frequency, EK of electrons equals to 0. If EK of the electrons is at 0, that means that according to the Einstein photoelectric equation, HF equals to phi plus 0 EK. And we'll call this F, because it's at threshold, we'll label it F0. So F0 represents the threshold frequency. Or, if we did it according to wavelength, it's hc over lambda naught is equal to phi plus 0 kinetic energy. So this is also the same equation we used in the last lesson at the end of the example to work out the threshold frequency. So the threshold frequency, or wavelength, can then be used to work out the work function. Threshold is used to work out the work function. And the work function is a property of the material you're using. So different metals have different work functions. That means that their energy wells are deeper or shallower. Now, these are not actual physical wells, but rather it's a representation of how much energy is needed to liberate the photoelectrons. So every metal has a different work function. And just to show you that qualitatively, the energy well of zinc might look like something like this. Again, this is a representation of how much energy. It's not an actual well, a physical well. And copper would have a deeper energy well. So that means that copper will have a greater work function than zinc. Copper will also have a greater threshold frequency than zinc. Now we can graph this. So what we can actually measure in this experiment is we can measure the frequency of the photons, because we know what the frequency is because we're generating the photons for a lamp or for a laser. And then we can measure the kinetic energy of the electrons coming out. If we plot this on a graph, where we do the kinetic energy on the y-axis and the photon frequency on the x-axis, we might get a line that looks like this. Now, this point here, where it intersects the x-axis, at that point we have zero kinetic energy. So that frequency is called the threshold frequency. So this is F0 for the red line. If we did the same experiment for a different metal, we will get a line that looks like this. They are always parallel, yes. So this is a different metal. And the blue line has its own threshold frequency, F0. Should really label it as a different letter, but it's fine for our purposes at the moment. Now let's consider how this graph has been drawn. So it's clearly following some form of the Einstein photoelectric equation, which is that HF equals to phi plus EK. Now we want to rearrange this to get it in the form of y equals to mx plus c, where EK is the y-axis and F is the x-axis. So when we rearrange that, it implies that EK is equal to HF minus phi, and then underneath that we represent it as a y equals mx plus c graph. So, well, that shows us that h, Planck's constant, is the gradient. That's why the second line is parallel to the first line. That also means that no matter what material I test this with, every single line will be parallel, because the gradient of the line is Planck's constant. It is a constant. It does not change. What does change, though, is the intercept. The intercept is given by what? The negative of the work function. So if we wanted to find the work function of this material using a graph, and we'll do it for the red one, we have to just extend this line until it intersects with the y-axis, and that value there gives us the negative work function. So you can do that with any line. Now I'm a bit aware that in the diagram drawn, the dotted line hasn't really come out as perfect as I wanted it to. It's a bit off, but it should just be that straight line carried on. Now we can set up a circuit that will let us find something called the stopping potential. And the stopping potential is the voltage required to stop these photoelectrons from being liberated. So let's turn to a new page. And this is the stopping potential. So we set up a circuit with a variable power supply, which means we can change the voltage. And we have a protective resistor in there. On this side, we have an evacuated tube, which is a glass tube. And what we do is we shine some light onto one of those plates. So these are photons. Now, if we ignore the variable potential difference, or the variable power supply in this question, or in this example rather, and we just assumed it was a circuit with no power supply, by shining light onto one of those plates, if that light was above the threshold frequency, that will emit photoelectrons. So that would cause electrons to leave that plate and fly towards the bottom plate. If that happens, then we end up having a current flowing through the circuit, because electrons from the top plate leave and they fly towards the bottom plate. They're absorbed by the bottom plate, and as this happens, it causes electrons to flow around the circuit. The electrons in the circuit are flowing around anti-clockwise, but conventional current is defined as what? It's the movement of positive charge. So the conventional current in this circuit, without the power supply, would be clockwise. So there'll be a clockwise current in the circuit. Now, electrons are negative. So if our circuit is set up in the way it is over here, by turning on this potential difference, we will end up having a positive charge on the top plate, and a positive charge attracts the electrons, which are negative. The work done by the potential difference is given by the electrical equation W equals to QV. Charge times potential difference is the work done. So if we're shining light and we have this potential difference, if the potential difference is big enough, it will stop the photoelectrons from being liberated in the first place. Because then the energy of the photons has to do work against that potential first, before it can liberate those photoelectrons. So we can actually use this to stop the liberation of photoelectrons. So I'm going to get rid of these electrons for now. So we write down, to stop the electrons, the potential across the plates have to be big enough that they cancel the kinetic energy. To stop the electrons, the potential at the plates have to be great enough to cancel EK. So we go back to our Einstein equation again. HF equals to phi plus EK. The potential difference we apply has to be equal to that kinetic energy in order to stop those electrons. And the work done is W equals to QV. The charge of an electron will denote it as E, so EV. And that is going to be equal to EK. So EK equals to EV. And the stopping potential, we'll call it V naught. This is stopping potential. And this comes from W equals to QV. This is the electricity chapter. Now we substitute that back into the Einstein equation. HF equals to phi plus EV naught. So if we wanted to find V naught, we divide everything here by E. That gives us V naught equals to HF over E minus phi over E. And this equation will find your stopping potential. You can also see that this relates to the previous graph where EK was on the y-axis. So if you know a value for EK, you can do EK equals to EV naught, divide that by the charge of the electron, and that will give you the stopping potential. Yes? Any questions? Say again?
What is E? Is it number of electrons?
E. Little e is the charge of the electron. So we can write that down as well. Little e is a charge of an electron. Charge of electron. And you guys already know that this is equal to minus 1.6 times 10 to the minus 19 coulombs. You have to know that.
They don't give us in the equation sheet.
You have to know it.
No.
You always have to know it.
Well, you didn't answer the question.
Basically, learn it because you don't want to waste time in the exam looking for things in the equation sheet. That will waste so much of your time if you have to do that for so many different things that you'll end up running out of time in the exam. And when you see exactly how many questions you have and the amount of multiple choice you have in the exam, those multiple choice questions will take a lot of time. Not all of them, but many of them. Any other questions? Ask a question.
Before the equations, how the hell does voltage stop energy?
Okay, so if there is a voltage, then that means there's an electric field.
Yeah.
If there's an electric field, if that plate is positively charged, it's actually attracting the electrons to itself. So you're giving the electrons some energy to escape the material, but that plate is positively charged overall, so it's also trying to pull the electrons back to itself. So you have to do two things there. You have to first do work against that, against the work function to liberate the photoelectrons, but then to make those electrons move, you also have to escape that electric field. Now, if that voltage is adjusted to the point where it stops those electrons from moving off that plate, yes, so the kinetic energy that the electrons would have had becomes equal to the work done, QV. Then the kinetic energies are cancelled because that's where the work goes into instead, is doing work against that field. And that then gives you your stopping potential. What potential difference you need to stop those electrons. Any other questions? That's the end of 2.2.1.